Hey guys, it's Devin, and today we're going to be working through a speed and average velocity example. So the problem reads, towards the end of basketball practice, an athlete sprints at a constant speed of 12 miles per hour from one end of the court to the other. Immediately afterwards, he jogs back to the starting point at a constant speed of 7 miles per hour. We're going to assume the athlete is traveling on a straight path, so this is going to be a one-dimensional motion problem. And we're asked to solve for the average speed and average velocity from start to finish. To better understand what's going on in the problem, let's go ahead and look at a diagram of the athlete's motion. Looks like we're going to be breaking up his motion into two separate paths. Looks like we have a path 1 and a path 2. So for path 1, we're going to be starting at his initial position, which is at point 1. We're going to be traveling the length of the basketball court, which is a distance d, to point 2, the other end. And then for path 2, we'll be starting at point 2 and traveling back to point 1. So in this case, his initial position is going to be equal to his final position. Let's go ahead and consider the speeds. So it looks like for path 1, we have a speed of 12 miles per hour. Let's go ahead and call this speed S sub 1, 2, where 1, 2 is indicating that we're starting at point 1 and traveling to point 2. For the second path, let's call that speed S sub 2, 1, so we're starting at point 2 and traveling to point 1, and that's going to be 7 miles per hour. We're not given any information for time, but let's go ahead and consider the time interval. Let's go ahead and call that delta t. Delta t is going to be equal to the total time. So total time. We can go ahead and break up the total time into time intervals by our paths. So for path 1, let's go ahead and call this time interval t sub 1. And for path 2, let's call this time interval t sub 2. So we can say that the total time interval delta t is going to be equal to t1 plus t2. Notice that for path 1, our athlete is going to be traveling at a faster speed than he is for path 2. So we can say that the time interval t sub 1 is going to be less than the time interval t sub 2. And I believe that's all we can really say about this problem so far. So let's go ahead and start solving this problem. Let's start with speed. And again, speed was going to be given by the total distance the athlete travels divided by the total time interval. So we know the distance d is going to be equal to 2d. And that's because we started at point 1, traveled to point 2. That was a distance d. And then we returned back to his initial position, so that's just d plus d equals 2d. So his total distance traveled is going to be 2d. For the time interval, we can call that t sub 1 plus t sub 2, the sum of the individual time intervals for each path. And let's go ahead and figure out what we're going to do with these time intervals. So we know that by this equation that speed is equal to distance divided by time. We can solve for time, and we'll have that time is going to be equal to distance over speed. So let's go ahead and make a substitution in. So for the time interval t sub 1, we know he was traveling that speed quantity we defined, s sub 1, 2. So we can go ahead and substitute d over s sub 1, 2. And for t sub 2, we can go ahead and substitute in that distance divided by the speed in that time interval, which is going to be s sub 2, 1. From here, if we're going to try to solve for a numerical value, we need to try to get rid of this d, and we can actually do that by factoring it out. It should cancel. So if we factor that quantity out, what we'll have is 2d over d times 1 over path 1 speed, s sub 1, 2, plus 1 over path 2 speed, which is s sub 2, 1. And sure enough, this quantity d is gone. From here, we can actually solve the problem for the speed. But you know what? Let's try to clean this up. So maybe what we might try to do is get a common denominator down here so that we can try to eliminate this complex fraction. So let's do that. So the numerator stays the same. We have 2. Our first term is going to be 1 over s sub 1, 2. Let's go ahead and multiply by s sub 2, 1 over s sub 2, 1. For our second term, let's go ahead and write that in. That's going to be 1 over s sub 2, 1. And we're going to multiply that by s sub 1, 2 over s sub 1, 2. And that's going to give us 2 over the sum of the speeds, which is going to be s sub 2(1) plus s sub 1(2), all over their product, which is just going to be s sub 2(1) times s sub 1(2). Let's go ahead and copy this and carry it over to a new page. We'll bring it over here so we have a little bit of room to work with. So from here, what we can do is we can multiply by the reciprocal, and we'll have that 2 is going to be multiplied by the product of the speeds, s sub 2(1) times s sub 1(2), and all of that's going to be over the sum of the speeds, so s sub 2(1) plus s sub 1(2). And here we have it. This is going to be what gives us our average velocity, or average speed. So let's go ahead and consider the units here. We're going to have units of speed multiplied by units of speed, so that's going to be units of speed squared. Over here, the sum of the speeds is just going to be units of speed. And this power 2 right here is going to cancel with our denominator, and we'll be left with units of speed, which is exactly what we expect for our answer. So let's go ahead and plug in some numerical values. So we have that the average speed is going to be equal to 2 times s sub 2(1), well, that was 7 miles per hour. That's going to be multiplied by s sub 1(2), which is going to be 12 miles per hour. And that's going to all be over their sum, so 7 plus 12 miles per hour. And we're going to find that our average speed is going to be 8.8 miles per hour. And this is kind of what we're expecting, right? Because we're solving for the average speed. So the speed for path 1 was 12 miles per hour. The speed for path 2 was 7 miles per hour. So our average speed should be somewhere in between, and that's what we got. So let's go ahead and start the second part and solve for the athlete's average velocity. So average velocity is going to be given by the athlete's change in position, delta x, over the time interval, delta t. And let's go ahead and consider his change in position. He's going to be starting off at point 1. He's going to travel to point 2 in this direction. Then he's going to return back to point 1. So in this case, his initial position is the same as his final position. Now displacement is given by the final position minus the initial position. And if these two quantities are the same value, then the change in position is going to be equal to 0, and whatever units you have in your problem. So in this case, we have this situation where our initial position is equal to our final position, so our delta x is just going to be 0 over the time interval delta t. So our average velocity is just going to be 0 miles per hour. And this was much easier than the first part of this problem. So the important idea to take away from this problem is to realize that velocity is not the same as speed. Speed and velocity are used interchangeably in everyday conversation, but to a physicist they mean two completely different things. Well, for one, velocity is a vector quantity and speed is a scalar quantity, so just by that alone they are not the same thing. But even if we don't consider the directional information for velocity, the magnitude of the velocity doesn't have to be the same as the speed. In the problem we saw that the speed, which was 8.8 miles per hour, that was not the same as the average velocity, which was given by 0 miles per hour. If you found this video helpful, please click on the subscribe button so you'll be notified when new videos are posted.